Based on the current power configuration, we calculate the flight performance during 3 phases: takeoff and climb, cruise, and turning. First, we look at the most important phase, takeoff and climb. In this phase, we evaluate the aircraft's obstacle clearance capability under full load, that is, how quickly it can reach a given altitude. During climb, the engine usually operates at maximum continuous power, which corresponds to a propeller speed of about 2,350 revolutions per minute. By keeping this speed constant and calculating from liftoff up to the cruise speed, we can determine the power available from the propeller at different flight speeds. In the takeoff configuration, it is necessary to determine the maximum lift coefficient, CL, that can be achieved within the critical stall speed range. When the aircraft pitches up, its speed naturally decreases. Regulations require the stall speed to remain above 18 meters per second. Although previous calculations with the improved airfoil gave a stall speed of 15 meters per second, we use 18 meters per second here as a reference to include a safety margin. It can be seen that when the aircraft climb angle reaches 19.5 degrees, the speed is close to 18 meters per second, and the corresponding CL is 1.38. Therefore, CL max is approximately 1.38. For the climb process, it is also necessary to establish the relationship between the angle of attack and the lift coefficient, CL. By setting the angle of attack, AOA, range from 5 degrees to 20 degrees, we obtain the corresponding CL-AOA results. A linear regression is then applied to derive the relation between the two. Here, results with CL greater than 1.38, that is, when AOA is greater than 13.35 degrees, are not considered, since this already exceeds the maximum lift coefficient for level flight. After adjusting the flight speed, the aircraft drag coefficient was calculated in the same way, taking into account the surface components. The overall CD of the aircraft is approximately 0.01788. To calculate the maximum climb rate, or the maximum climb angle, we first establish the equations using thrust, weight, lift, and drag. Considering that the takeoff climb angle is small, we can approximate cosine gamma approximately equals 1. Here, the independent variables are the flight speed and the angle of attack. However, several constraints must be taken into account. The upper limit of the lift coefficient is restricted by the stall angle of attack during climb, which is 13.35 degrees. The speed range is between 23 and 35 meters per second. The climb angle must be non-negative, meaning sine gamma greater than 0. Finally, within all the defined constraints, the maximum value of sin within all the constraints is 0.09121, corresponding to an angle of 5.2 degrees, with a climb rate of approximately 3.15 meters per second. Using maximum continuous thrust, the aircraft reaches 1,000 feet in 1.6 minutes and 1,000 meters in 5.28 minutes. In the cruise phase, the main objective is to calculate the appropriate angle of attack for steady flight without considering natural wind effects. By applying the balance equations, we can compute the corresponding flight speed and the required thrust at different angles of attack. Taking into account energy losses during flight, the cruise speed range is limited between 35 meters per second and 50 meters per second. The minimum cruise speed is set to 35 meters per second, which is approximately twice the stall speed of 18 meters per second specified for a Class 3 aircraft. This ensures sufficient safety margin, while also avoiding excessive induced drag that would occur at lower speeds. Here, the thrust is calculated from the difference between the velocity behind the propeller and the velocity in front of it, which is the flight speed. Interestingly, in order to maintain steady flight, as the flight speed decreases, as long as it is not too low, the overall kinetic energy decreases, and the required thrust also decreases, while the maximum available thrust actually increases. This allows us to select a suitable steady horizontal flight condition within the chosen speed range. Flying close to 35 meters per second results in relatively low total drag, making it a more economical option. Considering the effect of the centripetal force, the relationship for determining the speed is as follows. As we know, during a coordinated turn in flight, if stable flight is maintained, meaning that gravity is balanced, then the faster the speed, the slower the turn rate, and the larger the turning radius. Conversely, at lower speeds, the aircraft turns more quickly and the turning radius becomes smaller. Taking full load as the reference, the maximum bank angle in turning corresponds to a 10-degree opposite deflection of the lateral flaps. At this condition, the distributed lift coefficients of the aircraft as well as the total lift coefficient can be obtained. With this lift coefficient of 0.35, the minimum turning speed of the aircraft must be greater than 39.3 meters per second in order to maintain a stable turn. From the turning speed formula, a series of calculations can be carried out to obtain the corresponding turning radius and turning time. Here, the minimum equilibrium turning speed can be determined using the balance equation. When looking at the turning load factor n as the turning speed increases, even a small increase in bank angle can significantly raise the load on the wings. This means that the maximum speed must include a sufficient safety margin. Thank you again for watching. If you are interested in the Lavion Ideal channel or would like to follow the guidance from Lion, don't hesitate to subscribe. See you next time.